Hello and welcome to today's Wolfram Institute live stream. Today we're joined with Vit Tuček. Hope I'm pronouncing that correctly. A mathematician and researcher.
Like two checks.
Tuček.
So Tuček.
Tuček. All right, thank you. Mathematician and researcher in Prague, experienced with differential geometry, representation theory of Lie groups. And today he will be talking about complex Grassmannians for wireless data transfer. Vit, take it away.
Thank you. Thanks a lot. And thank you for the opportunity to speak here. I'll be alternating between my slides and Mathematica notebook. So right now you should see my slides. And the rough outline is first I'm gonna give you some introduction to wireless communication, and then we will look at this idea of Grassmannian communication, which is this application of Grassmann manifolds for wireless data transfer. And then we will, I will showcase some results of mine and my colleagues. This work was done when I was working in Huawei Stockholm R&D, and it was a joint project with University of Cantabria. So these are my collaborators, two guys from Huawei, Gunnar Peters and Olivier Verrier, and from Cantabria, Diego Cuevas, Javier Alvarez Visoso, and Carlos Beltran and Nacho Santamaria. I have to say, I'm a pure mathematician by training, and this was my first foray into serious applied math research. So, all mistakes are purely mine. So, okay. How do we send data through, well, let's say through wireless channel or through a cable? We are using electromagnetic waves, and there's always 2 degrees of freedom. So, for example, there is amplitude and phase, or amplitude and frequency, and so on. So you pick some kind of modulation of these electromagnetic waves, and you pick a finite set of complex numbers corresponding to these 2 degrees of freedom. So these complex numbers are just like a convenience of packing 2 degrees of freedom per one electromagnetic wave, right? So you pick some subset of these complex numbers, and you label them by zeros and ones, right? So this is like a 2-bit constellation or 2-bit codebook. This is a a slightly larger one with 2 bits, and this is like a 4-bit codebook, right? So just modulating the wave by parameters corresponding to this point will mean at the receiver, okay, you have just been sent this bit string 1000, right? So,
right. And that's a way to increase the bandwidth for the transmission, right? So you have
yes,
a waveform,
exactly,
and you can read off
exactly.
its amplitude as well as its phase. And then if you have well-defined control over the phase and amplitude, then you could.
Yeah, exactly. Of course, if you pick a bigger codebook, you will have more points. You can send by just one modulation more data. So the way it works in practice is you have these like assigned time slots. So let's say you are sending, I don't know, let's say 10 milliseconds. And in those 10 milliseconds, you are modulating with this point. And in the next 10 milliseconds, your bitstream continues like this. So you are sending this point. And the receiver has these 10 milliseconds to kind of sample the electromagnetic wave and reconstruct the bits that this bit string that you have just sent, right? So I hope I will be able to kind of show you how it's done here. So what we will be using for this example is this QAM modulation, quadrature amplitude modulation. This is how it looks like. So you have these 2 parameters I and Q, and you just take this superposition of sinus and cosinus with these 2 I and Q components, and this FC is so-called carrier frequency. So T is this time, so this IT QT, you can think of it as piecewise constant function, and FC is the carrier frequency of the wave that you are sending through your antenna. And so this is how it looks like. This is like 16 QEM. Can just maybe, oops, that's maybe too much. Yeah, that's probably way too big. Yeah. So far so good, right? So what happens in this wireless channel? What happens in the media? So the basic model is this one. Just you are sending X from some QEM constellation like this, and you have some kind of distortion coming from the environment, right? So there can be, some kind of occlusion, some kind of maybe reflection or something, and that's manifested in this linear term, this H, so-called channel coefficient or channel matrix later. And this N is just the Gaussian noise. But because we have like complex valued variables, it's complex normal distribution, right? So it's really just 2 by 2 or two variate normal distribution with identity matrix as variance. And so this is how it looks like, right? So these red points are the ideal images of your QEM constellation, and these blue points, these are what you really measure on the receiving end, right? So when I increase the noise variance, it kind of, it's kind of blurry. It kind of melts together. If the variance is small, you see well-defined clouds. Like, okay, if I measure this, it's pretty clear that this is what was intended to be sent, right?
Mm-hmm.
So that's kind of the intuitive idea behind this. In practice, in this model, we normalize X to be of in the unit disk, let's say, and then we have some kind of row here. That changes the variance, and this is like the signal to noise ratio, or this kind of factor. In practice, what we are really changing, because the noise is the property of the environment. In practice, what we are changing is the norm of your QEM constellation, and that translates really physically to just increasing the power on your antenna, right? So like this whole equation is like scale invariant. Like you can either fix. So what really just matters is the ratio of norm of X and the variance here, and we can just normalize it like this. So this is the SNR vector, and so even though here it's kind of blended together, you can still kind of decide for most points where they belong, right? And it's only these bordering points where we are not sure. So we make mistakes, right, when we guess. And of course, there's a whole big business of how to label these constellations efficiently, because this is like on the lowest stack of the whole technology, right? So you are sending some bit stream, but it doesn't have to be your raw data. It goes through some error correcting codes and so on. So what you really want is these mistakes to be easily repairable by some error correcting codes. So it's a whole another problem to consider.
Right. So
And
that's like the phi layer, as they say, the physics layer of the network stack.
yeah. And another thing is that this H factor is not really deterministic either, right? I mean, there are some slight variations. Let's say the signal is reflected, that you are not receiving just direct line of sight signal, but it gets reflected by some building or by some moving car, and this creates some changes in this H. So usually people, like the two simplest models is H is just randomly complex normal, that's so-called Rayleigh fading, and that corresponds to some kind of occlusions. So that is mean zero. So there is like no direct line of sight. You are receiving it just through some kind of difficult terrain. And then there is region fading, which is really a direct line of sight, which has mean one. And this is what it does to to the images of the Quam constellation, right? So this is the rich in fading. This is fine. And we are now obtaining these blue clouds around one of these points, so we are still kind of in the clear. But with rayleigh fading, you get weird patterns like this, and yeah, it's a bit of a mess. So that's the situation that we are in. We have this model, and now we want to decode the data. So first, what we need to do is okay, intuitively, it's kind of clear what needs to happen, right? Like we have these Voronoi cells, and if we measure this on the receiver, some small blue point like this, we just look at the closest red point to it. But as you mentioned a few minutes earlier, we need to increase the number of points to have higher bandwidth. So here we have 16 points. So going through 16 points and measuring the distance from our received blue point, that's easy. But imagine that we have like 256 or maybe 1024 points, these big red points, right? And so you have to do these simple enough calculations, but 1000 times every 10 milliseconds, right? And it's not the only thing that you need to do. You need to do a lot of stuff, like sampling and analog digital conversion and so on and so forth. So like your goal is to find the red dot as fast as possible, right? So the idea is, okay, first, and anyway, this H was simple enough, but when I distorted a lot, then okay, well, like I have no idea what's going on here, right? So what I need to do is I really need to estimate the channel. I need to estimate H. And yeah, that's really just ordinary least squares. I mean, you can do some fancy stuff, but basically you can do just least squares or maybe with Tikhonov regularization. And that works quite well. Like, already, okay, I picked here some noise variance, which is quite low, but okay. And here we already with two samples, we have like 3% error, right? And it decreases like with 8 samples, we have less than 2% error and so on. So the way it works in practice is, you turn on your mobile phone or maybe your Wi-Fi router or whatever. And first there is like a handshake and some like technical communication is going on before you can start sending data. And one of these things is sending pilot signals. So in the free GPP standard for wireless communication, we have these so-called pilot signals. You can just imagine, okay, in the beginning, we are sending this uppermost, like this point from the Quam constellation like 10 times, like, right? For the first 100 milliseconds, we will be sending just this. And your device knows it. And so when we know what is X, we measure Y, and we just estimate H using ordinary least squares, right? That's what's going on. Makes sense?
For the handshake?
Yeah.
Mm-hmm.
Yeah. Yeah.
Yeah, so they negotiate on this is what the transfer rate is going to be. This is my
part of the standard
signal timing and all that stuff.
Yeah.
Mm-hmm.
Exactly. And once you have this estimated H, you can just divide your true H by this estimated H. You can kind of try to undo this X times H stuff, right? You just take 1 over H. and that works pretty well. Like it kind of moves your like tilted and rotated constellation. It moves it. Okay, I really need some bad sample here. Yeah, so okay, so this is a good estimate. So even with pretty high noise variance, we are kind of realigning the Voronoi lines to the original lines. And what it means is that now when we measure, we just, kind of coordinate wise round. It's very like if you look at this operation now, like looking for the closest red point, because these Voronoi cells are almost the perpendicular lines from our axis, we can really just do some kind of bit operation to kind of move the blue point directly to these guys. It's like really simple circuitry. And yeah, so I created this thing, and maybe you can see a little bit better what happens when we misalign. So basically, these misalignments, that's what creates the error in the detection. Right. For example, here it would be quite bad because this is already after the rotation. Like we are supposed to be here on the perpendicular line, but we are really here on the blue line. So these like misalignments, that's what creates the errors in the detection.
So why would it come in tilted in the initial why is
Sorry, that was a bad choice of word. It's not tilted. It's really just scaled and rotated.
why is the why is it rotated?
Because even the channel is a complex number, right? So yeah, you just write this in polar form. So this R factor from polar form is your kind of I forgot the term. It's like that's what kind of blocking your signal, and then there is this exponential term or this phase term that rotates your constellation, and that's pretty much like a phase shift, right? When it acts on your real complex waveforms, and that's I guess from the reflections.
Bouncing off surfaces for the wireless signal, for instance.
Sorry?
Bouncing off surfaces in the wireless signal, for instance.
Yes. Okay. And interestingly enough, like here what I did, like I calculated the probability of error for each of the Voronoi cell. And you can see here it's not really symmetric or like uniform. It should be symmetric, but it's usually not because our estimate is not great. And it's not uniform either because like these points closer to the origin have different properties than points further from the origin. So what we are looking at here is like probability of misdetection when this QAM point was sent or this QAM point was sent and so on. So this is wireless transformation up to the year, let's say roughly 2000. And then the engineers figured out that they can exploit this phenomenon of measure concentration for high dimensional Gaussian distributions. So what's going on is that if you add antennas, your model can stay pretty much the same, right? So let's say we have m antennas at the transmitter and the same number at the receiver. And now each antenna, let's say Y1, obtains a superposition of the signal from each of the transmitting antennas. But since these antennas are, like physically displaced from each other, their channel coefficients can be a priori different. So you really have like a channel matrix H. That's for each receiving antenna is mixing all the signals coming from all the transmitting antennas, right? So in general and in practice, you do have different number of antennas on the transmitter and on the receiver. But for simplicity, we will just, I guess, for most of the talk, stick to the same number of antennas. And like the basic model would be, okay, these are all uncorrelated, these signals. In practice, there are of course, some correlations, right? Because, pretending that when we are sending something from two antennas which are like centimeter apart, that it will be very different or independent is silly. But these correlation matrices, they don't really, I mean, they complicate things a lot. So like for simplicity, for now, let's say that there is no correlation. So this idea is to increase the number of antennas, and that has several good reasons. Because when you look at this norm of the channel matrix, just the squares, sum of squares of the absolute values of the entries, that corresponds like to the to what your environment does to your signal energy-wise, right? Like if, as we have seen above here, when we have just one antenna with rarely fading, when there is no direct line of sight, the signal is attenuated, like the energy goes to zero, and we have a hard time recovering the signal. But if we add more antennas, like here, we add more antennas, and we look at what it's doing on average to the signal, the variance of what it can do is decreasing towards one, or not decreasing, but concentrating on one. And it's really this concentration of measure phenomenon. Here you can see it a little bit better. This is just the average of the square of the norms of the channel matrix. For one, you have a lot of these guys which are close to zero for just one antenna, but already for let's say 8 antennas, right? You have quite nice concentration here, and there is almost no cases where the realization of your channel matrix would kill your signal completely. That just doesn't happen, right? So that's the idea. And another thing is, if you look at the noise is again just complex random normal. So there's the same phenomenon going on. And so in some sense, the noise kind of starts behaving more deterministically. You can really just think of it as some kind of random shell displacement. And that simplifies the analysis a lot. And you can exploit this, what they call noise hardening, in something called beamforming, which means that you kind of program your antennas to send the signal not like to all directions at once, kind of form a beam towards your receiver, right? So there is less interference, which again leads to like more stable communication, higher bandwidth, and so on. And last but not least, the Shannon capacity of this channel scales like this, scales with the number of antennas pretty much. Yeah. So, twice as many antennas, twice bigger bandwidth. Great. And this kind of leads us to geometry already. So this is where we are at. We have some M transmit antennas. Now, for each coordinate, we can do the Quam constellation or some other constellation, or maybe we start to pick constellations not coordinate-wise, but maybe on this whole vector space CM, like not picking just complex numbers, but really complex vectors, right? But again, decoding can be expensive, and so on and so forth. Lots of papers written about this. We have the received symbol or received signal with a priori different number of antennas. We have the channel matrix that mixes the input, the transmission, and we have this wide Gaussian noise. And the model is formally kind of the same, right? Y equals x times h plus noise. And the thing is that when you do like 2 antennas at the transmitter, 1 at the receiver, things are easy. When you do 4, 2, 4, 4, things are easy. But with 6G and with some special applications like antennas for, let's say, football stadium, right? You have 20,000 people there, and everybody wants to take a photo of the players celebrating. So they want to do like 128 antennas, or a huge number of antennas. And so, as you can imagine, you have a lot of linear algebra coming in for decoding and stuff like that. And that kind of becomes prohibitively expensive. And that one of the most interesting features of this job for me was that it kind of hits the spot that seems to be missed by mathematics, right? Like you have this, let's say, everyday linear algebra that's taught like in normal courses, and then you have this numerical analysis style of algebra that's for like solving PDEs and stuff like that, or doing like large scale calculations for data analysis. And these scientists, they usually care about like machine precision or close to machine precision. They care about the huge systems of linear equations. But here we have, relatively speaking, small system. We have age that's of 16 by 16 or 32 by 128, something like that. It's not a large matrix. And we don't need it, we don't need this, for example, this least squares for estimation. We don't need it to machine precision. We just need it good enough, right? We are fine with 2% error. It's okay. But we need it fast, right?
Mm-hmm.
We just need it within like 100 of milliseconds. So it's kind of like missed area in math, it seems. And the idea in Huawei and elsewhere, I guess, was okay. Let's look at it from the geometric viewpoint and maybe try to apply some ideas from geometry and see where it can lead us. Hoping that with more complicated formulas, you will not have to wait those extra milliseconds longer. So where does the geometry come in? So one thing is that even this channel matrix can depend on time, right? Because the objects are moving. Like you can be moving in your car or in the train, or the reflections can be from moving objects, or from the like a storm cloud or something like that. So it changes in time, and usually these antennas they send on different frequencies, and so really what's H in practice is not just one matrix, it's really a surface in matrices, which is indexed by time and by frequency. And that means that you can start to look at things like, okay, can we do interpolation in time? Can we do extrapolation in time or in frequency? What's going on? In practice, you do care about these covariance matrices, right? So this is really like where is it? Yeah. Okay. So in practice, you don't have 0, 1 here. You just have like a matrix valued random variable with some non-trivial covariance structure. So this is like transmit correlations and receiving correlations. And of course, you can exploit these in your data transmissions. But again, these are really, surfaces or lines in what, right? So these are covariance matrices. And so they live really in the space of positive definite matrices, which is a symmetric space.
Yeah. So I have a
Right?
question.
So this is,
If I may, you mentioned
of
100
course,
millisecond. Is so you have all these antennas transmitting, and then all these antennas receiving, and then for each one of those, you have to make adjustments. Say like this antenna receiver pair has a certain noise profile, and you have to correct for that and get the variance down so that you can get the phase amplitude modulation buckets well defined. Is that accurate?
Yes.
Okay.
Yeah.
And then
That's pretty much my understanding. Yeah.
and so
So
the analysis of the signal analysis for those corrections, is that what has to be done within 100 milliseconds or every 100 milliseconds, or what is it? What does that
okay,
time scale
that's
mean? Because it seems like a long time, 100 milliseconds.
yeah. Sorry, I have to say you have to take these numbers with a big grain of salt. So I was working in like different area. So I don't know if it's 100 milliseconds or 10 milliseconds. And in practice, there are a lot of obstructions basically by hardware design, right? So for example, you can imagine that you don't have to estimate age at all. You can start just with blind guess and let the feedback from the error correcting codes tell you what was really the correct signal, that you are starting to guess. Like you use some kind of Bayesian approach, but that's like a no-go because of the hardware, because you want to modularize the whole system, right? So there are all kinds of like hidden obstacles like this. And I forgot to say that all the time I'm talking just about P2P communication, like peer-to-peer. You can have also communication with multiple receivers, like broadcasting, or you can have communication where you have multiple um, transmitters, right? Like just gathering data on the same channel from a lot of uh, transmitters which are not collocated. So this is kind of like the simplest model for the communication, and it's already kind of bad enough to give you some idea how stringent the real requirements are. There were some colleagues in Huawei who were just, this is our algorithm for estimating the channel, and we have these temporary variables, as you do. And now let's try to figure out how many bits can we afford to shave off each variable, right? You have some temporary variable x, and okay, x doesn't have to be maybe 32 bits. Maybe it's enough if x is 6 bits, right? So they were really shaving off bits so that the resulting hardware, because that's in the end implemented in hardware, so that the resulting hardware will be more power efficient and has like a uh, shorter pipeline, so to say. Like not when you operate on more bits, it kind of creates few extra, I don't know, microseconds maybe, but it can add up, right? So I was working at this abstract level, really not thinking about hardware or on antennas that much. I was just had my complex vectors, I had my complex matrices, and then I was thinking, okay, now we want to interpolate, extrapolate maybe this matrix, maybe these covariances. So for example, these covariances, they live on this symmetric space. So it's a group of non-degenerate complex matrices, quotient out by the group of unitary matrices. And but now you have, okay, so this is a symmetric space. So we have a nice Riemannian structure here, but there are various invariant distance function, for example, here. So like, what is the correct one to pick for the problem, right? And what about degenerate situations where you have like complete occlusions or complete correlation and so on? So it was like one set of problems to estimate better these covariance matrices. And another one was had to do with this beam forming, or sometimes it's called pre-coding. So the idea is, okay, we have this age estimated at the receiver, but if the transmitter knew age, he could use this information and he could exploit it to send data more efficiently. So instead of sending just X, he could use some kind of pre-coding procedure W. So these are some examples, like this zero forcing or MMSC. And really the ideal case, like these are practical used examples, but the ideal case has to do with singular value decomposition. And you can actually see these cases as just kind of approximations to singular value stuff. And what it means that you do SVD decomposition of your channel matrix, which means that V and U are unitary matrices, and D is diagonal matrix with positive numbers on the diagonal, these so-called singular values. And then you just kind of do this mathematical change of variables of your model to the basis given by V. You will see that first of all, it's a unitary change of basis. So this noise is still complex normal distributed. Like action of the unitary group doesn't change the distribution of the noise because it's like symmetric from the get-go. And so you have now just y tilde 1 equals x tilde 1 times d1 plus noise. y2 equals x2 times d2 plus noise. And now you see when the noise is bigger, or when the variance of noise is bigger than the singular value, you have really poor time. You will have really poor time recovering that particular x value, right? Make sense? Like if you were sending these coordinates with respect to this singular vector basis, then all the coordinates that correspond to small singular values, small meaning smaller than the variance, they will be hard to recover, right?
Right. There's noise down there.
Yeah. So what you want is you don't really need to send the whole big H to the transmitter. You just need the major singular vectors there, right?
Mm-hmm.
And once the transmitter knows the singular vectors, he can use it to basically transform QEM to something else before it's gets sent out of your antennas, and the receiver will know that this happened and use that information to decode properly, and it will just better utilize the available resources, right? You can think of it as concentrating the power on your antennas so that the power is allocated only so that we are kind of missing the noise somehow.
That's
And
interesting. So the transmitter will send out like a test signal, and the receiver will analyze it and read off the environmental perturbations, and then send that information back to the sender so that the sender can pre-adjust for that transmission.
Yeah, exactly.
So exactly. I could see this being like really good for, I don't know, an in-home network with like a laptop that's sort of like being in one room, and then the router is like in a different room, so it goes through this wall, and it's sort of a static situation. But is this employed for like wireless communication, like cell towers, when you're like driving in your car?
Yes.
Oh wow.
Yeah, so I think that's exactly the problem that's being solved right now. So they are trying to implement it and trying to implement it so that it really works somehow. Because okay, I'm not sure what's the implementation status right now. I just know that this is taking a lot of resources in Huawei, Ericsson, a lot of universities. Yeah.
And all this calculation is being done. Where is that being done exactly in the network stack? Is it done like on the
so that's another
or layer one?
So cell towers. So like here you would imagine cell towers, right? So the receiver is your mobile phone. Your mobile phone estimates age. sends back to the cell tower, hey, my singular vectors are these, and the cell tower uses this information to send data to you more efficiently. And that's one of the reasons that why they really need like power efficiency at the cell towers, because I mean with these more antennas and bigger matrices, it's actually a lot of calculations. Yeah.
So
Okay.
one question. So these antennas, I should imagine them at least at the receiver like being close together in one device, right? But on
Yes.
the transmitter, they must be close together, or is it they can be arbitrary, and this method would also work because each of them is sending the same thing, or how is it?
No. As I mentioned before, you should really imagine this collocated, both at the transmitter and the receiver. You can imagine that there are multiple transmitters with different H matrices, and you can also imagine that there are different receivers with different H matrices. That's so-called broadcast, and the former one was multiple access channel, and that leads to like whole another set of problems. So we dealt with that as well, but just for simplicity, I decided to stick with this P2P.
So like the condition is that they are close together so that there is the same it can be used to estimate one H matrix. Okay.
Yeah, but basically you hope that H will be, like this probabilistic model will be a good fit for your H. That's what you imagine, right? So maybe not instead of like sigma squared identity matrix here, you would imagine something like RT times some sigma squared times RR, something like that. But when you have them further apart, there's I guess no hope of obtaining like a good working model with just this assumption that all of these channel matrices, which are not really coming from collocated antennas, that they follow exactly the same distribution in the same way. Yeah. So okay. So what are the singular vectors? They are just the eigenvectors of H times H Hermitian conjugated. And so then, that means that they are really just defined up to non-zero complex multiple, right? So you really should not speak of singular vectors. You should really speak of singular lines, right? And so in particular, with just one singular vector, you are really looking at the space of lines in CM, otherwise known as the complex projective space. This is one example of a Grassmannian. It's an example of symmetric space, which is the quotient of these two Lie groups, unitary matrices of size m by m, and then like let's say upper left vector would be u1, and then lower block right vector um minus 1, and then like these two, like the rest of the first row and first column will be zeros. So this is like a subgroup of this guy, and this is the complex projective space. And as I mentioned before, we are really looking always at this in time and frequency. So okay, we know that when we are sending on this carrier frequency, we have this singular vector. What if we are just few megahertz to the right or to the left? Is it the same? How do we extrapolate? And bearing in mind that we are really just moving in this complex projective space, not in a vector space. And if you look at multiple singular vectors, you have this kind of symmetric space. You have just more these U1 vectors, and you have smaller big block. And if you have multiple singular values, you have these things. So like one part of the job was really looking at these manifolds and trying to figure out some kind of random processes on these manifolds or interpolations on curves in these manifolds and so on.
So the matrix that you're calculating, that you need to calculate, it's not one particular matrix, but it's an equivalence class of them. If you get one in the equivalence class, you're golden, right?
Yeah.
Is that the idea?
Yeah. Okay. Okay. Grassmannians. Yeah. So I kind of forgot to add some slide here, maybe. No, it's here. Okay, perfect. So so these things, like these curves on manifolds and so on, that was really not the main part of my job. The main part of my job was this usage of Grassmannians. So let me explain. Okay, how does it work again, right? We turn on the receiver, we have this handshake, they exchange the pilot signals, and then we start sending data. And let's say my receiver is moving. I'm sitting on a train looking at cat videos, right? And the train takes a turn, and the channel matrix changes, and suddenly, I'm not really decoding properly. So, there is a part of the protocol that dictates, okay, when the error rate is too high, send more pilot signals, estimate again, right? So, for a while I have blockiness in my cat videos. Then because some part of the channel is used for these pilot signals, then I re-estimate age. Great, I can look at cat videos in full HD again, and then the train takes the next turn. And you can try to mitigate this with these extrapolation techniques and so on. But the problem is that sometimes, especially in urban environment, like there are really sharp turns, there are big buildings which creates complete occlusions and so on. The problem is that sometimes you really need to estimate or re-estimate completely from scratch. And estimating, let's say my phone has, I don't know, maybe 2 antennas. The cell tower has maybe 4, I don't know. But let's say right now when I take a turn in a tramway in my town, my phone has to estimate age, 8 complex numbers, right? But when we want to add more antennas to watch, I don't know, get videos in 4K resolution, it will not be 8, it will be, I don't know, 16 times 4. That's suddenly much higher number, right? It grows quadratically. And so it seems that when we continue on this path, we will use like a disproportionate fraction of our allotted milliseconds just to estimating the channel. So Grassmannian signaling is this 20-year-old idea that says, okay, look, we are pretty much always assuming that age is almost constant for some period of time. Let's say for time enough for T transmissions, right? So what we are really doing when we have age, we estimate y1 from x1 with age up to yt from xt with the same age. So what we can do is we can just stack these vectors on top of each other and think of it as a matrix, right? So we have T by M matrix that was sent to us in this time for T transmissions, and we received T by N, right? And if we look at this and we imagine that M is equal to N, that these matrices have the same shape, we may notice that the space spanned by the column of X, if there is no noise, forget the noise. I actually wrote it here. Yeah. So the space spanned by the columns of X is the same as the space spanned by the columns of Y, as long as H is non-degenerate. That's always true, right? Because if H is non-degenerate, we can just hit it. Yeah, I think it's clear. It's like basically linear algebra, right? So the idea is, okay, we are always assuming this anyway, that there is like H almost constant for T transmissions. And when we, instead of looking at the values of these vectors that were sent to us, we look at them as matrices and we look at their column spaces. They are the same spaces no matter what H was. So we don't really need to estimate H as long as we encode our data into column spaces, right?
So X and Y
So
are
the
different bases on the same subspace of C.
yes, yes,
C,
exactly.
C times M.
Exactly.
Okay.
So this is my poor illustration of this. Instead of sending this QAM vector, we are sending this line.
Mm-hmm.
And because of the noise, I might receive line coming, coming from the origin through some of these red points. But it's pretty clear that when I look at the distance between these two lines measured by the angle, it was this line that was being sent, not this one, because that's much further away, right?
Right. Again, yeah. So
So
this is up to this is a complex line, I guess. So up to U1
yeah,
symmetry.
yeah, exactly.
Okay.
Exactly. It's complex.
Mhm.
Everything's complex, so it has to be complex lines. Okay. So if we have M antennas, and okay, from now on, assume that T is bigger than M and N, right? So that we have like tall matrices. So we are looking at this Grassmann manifolds. By definition, these are as a set, it's a set of subspaces of fixed dimension, right? So we have T-dimensional vector space, and we look at all possible subspaces of dimension M. And you can put some topology on this set. You can put a smooth structure on this set, and it's a nice smooth manifold. It's actually also a smooth algebraic variety, and so on. Like there's the huge literature on these beasts from all angles. So as a homogeneous space, it looks like this. And it's almost like the space of M singular vectors, except for the M U1 vectors, we have like a whole big block of UM.
Yeah, it's
And
interesting. So
here are
yeah, just for the sake of our audience, I mean, so if you look at all the lines, for instance, through the origin, so like you're looking at linear spaces, and if you want to look at the collection of these linear spaces, for instance, on the plane, if you're considering lines to the origin as like the classic example,
Mhm.
the lines to the origin, all that the only thing that changes between them is the angle that they make, right? And so
Yeah.
if you imagine just spinning a line around the origin, then the space of lines to the origin on the plane forms a circle. So you have a collection of linear spaces being a curved manifold.
Yeah.
And
except except there is one caveat.
mm-hmm.
Like when you rotate the line, it's kind of like 2 to 1, right? Like if you take oriented lines, then you have like circle. But if we don't have any orientation, like we just have the line. So the line that goes from lower left to upper right, and we rotate this other line here, is really the same line, right? So
Right.
we
Well,
are really looking at like a half circle whose endpoints are kind of joined. So, yeah.
Yeah, you could rotate
So
180
in the
degrees
circle,
to get the same infinite
yeah,
line.
yeah.
And
So
then
these complex these projective spaces are kind of more complicated from topological viewpoint. I mean, yeah.
right, it gets incredibly complex when you start trying to parameterize, let's say, all the planes in 3 space.
Yeah.
Yeah.
So
thing. And then
so I actually wrote down some other realizations of these, which are quite useful, right? Because like the definition doesn't really tell you much. Okay, we have this set of subspaces of fixed dimension. How can I tell when the two subspaces are close to each other or far away? I it's hard to get from the definition. With this homogeneous space quotient, of two Lie groups, you have some general machinery how to do that, but that's like fancy advanced math. But the point is that you can do it much more kind of down to earth way. So, you can just represent these subspaces by a basis, right? So let's look at some tall matrix as we had before, and let's say it's an orthonormal basis of the subspace. So you identify each subspace, or you pick some basis in each subspace which has orthonormal vectors. But there are lots of such bases, but they all differ by multiplication by some unitary matrix, m by m unitary matrix. So it's already like one step better because you are still portioning out some action of a Lie group, but on much more manageable space. There's something even better. It's these two lines. You can identify the subspace with a matrix that projects to that subspace. You just take the orthogonal projection to the subspace. What is a projector or a projecting matrix? It's symmetric or Hermitian symmetrics. Its image is the whole subspace, so the rank of the matrix is exactly M, and p squared equals p. That's this projection property. So in other words, we are just looking at symmetric matrices that satisfies these two equations. Because of this squaring property, p squared equals p, you can replace this rank condition, which seems complicated, with a very easy trace of the matrix equals M.
By p squared, are you talking about a dot product there?
Sorry?
Are you talking about a dot product for that p squared?
No. It's really just matrix multiplication.
That's what I mean, dot product.
Okay.
Yeah, matrix multiplication. Yeah, it's written in dot.
Yeah, I forgot to live in Mathematica worlds.
In Mathematica,
yeah.
to multiply two matrices, there's a notated.
Yeah. I know. I just.
Okay. You're right. All right, we're good.
Yeah. So really, this is just a composition of two projections. Is this same thing? And on the space of symmetric matrices, you have this so-called Frobenius inner product. So it's just trace of A Hermitian conjugated times B, and you can look at the norm induced by this inner product, and it's really just Euclidean norm on the entries of the matrices, right? And this leads to this beautiful picture that I stole from this book by Conway, Hardin, and Sloan, packing lines, planes, etc., packings in Grassmannian space. You have this space of symmetric matrices. You have these conditions trace P equals M. So we have like hyperplanes given by this linear condition trace equals something. And then they use some kind of shift. Basically, what they explain is all these Grassmannians live on a sphere. So like Grassmannian of n-dimensional subspaces would be on this intersection of this big sphere with this hyperplane, right? And there's a nice duality between these spaces. Like if you have subspace of dimension m, you can take the space which is orthogonal to that, and that's a subspace of complementary dimension. And in this picture, it's really like a central symmetry through this point in the middle of the sphere. So you can realize all these Grassmannians together in a nice Euclidean space with nice inner product as some algebraic subvarieties of spheres, right? Of these intersections of hyperplane and sphere. And the equations are very simple. P squared equals P, right? Mm-hmm. It doesn't mean that these spaces are, like simple or it just means that you can just write down the equations in this nice compact form, and it's quite useful for calculation. So this is like
P squared equals P. That means as a projection operator. I mean that as a linear, as a transformation. That matrix represents a projection.
Yeah.
Mm-hmm.
Yeah.
Yeah.
And so this okay, now two important things. So first of all, you have some kind of okay, from this realization, it's also not so hard to prove that this subset, this algebraic variety, is actually smooth. That's one thing. Another thing is that okay, we have a smooth embedding or smooth subvariety of some space with an inner product. So this inner product induces Riemannian metric, and it induces exactly the Riemannian metric that makes it this symmetric space. So the metric abstractly induced from this Lie theory machinery is the same as the one that you get from this nice simple inner product when you have this nice embedding. And another thing is you can just measure the distance between 2 points here by the norm induced by this inner product. And that's so-called chordal distance, because it's really like a chord here, right? You have 2 points on a sphere, and you measure the distance not along the sphere, but directly through the space, like putting a chord into the sphere and measuring that.
Right.
So this is so-called chordal distance, and yeah, I'm kind of running a bit late, so maybe I should speed it up. If you have any questions, don't hesitate and ask me. The Riemannian distance, the chordal distance, and pretty much all the distances that you can think of on the Grassmannian, which have good invariance properties with respect to this Lie group action, they come from so-called principal angles. So principal angles, they generalize this notion of angles between lines, and computationally, you get them from, again, singular value decomposition. So if you take two subspaces, now this UV are always these projector matrices. So you have two projector matrices, U and V, and you calculate singular values of this U star times V. And these are all positive numbers, and these are cosines of the so-called principal angles. And these are really just the generalization of the angles between lines, and you can also define them without, invoking this magical SVD thing of this guy. You can just say, okay, let's take one line in U, another line in V, and let's look at the largest angle between two such lines, right? So you are kind of optimizing over all pairs of lines, first one from U, second one from V, and you are looking for the largest angle. And that will be your first principal angle. And then you take orthocomplement of these lines within these subspaces, and you reduce by that dimension by 1, and you just repeat this process, right? So that's the principal angles, and there are several different distances used in the literature on Grassmannians, but we will be mainly using this chordal distance for completeness. The geodesic distance coming from the Riemannian structure is just sum of squares of the angles, right? So you can see for small points, it's almost the chordal as it should be. Like when we have 2 points which are close to each other on the sphere, we can approximate the distance rate just by measuring in the ambient space. Okay, so where we are at? Classically, we are sending these vectors, and we stack T of them on top of each other, and so we have this matrix X, and each entry is coming from some Quen constellation, right? That's what we are doing classically. And now we have this Grassmannian, and we have pretty much the same degrees of freedom. So here our matrices have m times t, dimension m times t. Sorry, yeah. The Grassmannian has smaller degrees of freedom because the dimension is smaller by m squared here. That's this UM factor coming in, right? So these matrices, t times m, but we are quotient out by a Lie group action of a group that has dimension m squared. So it seems that we have less degrees of freedom.
That's good.
But if we account for the pilot signals, okay, because the problem is, okay, we are moving in this urban environment, we are taking sharp turns and so on and so forth. So if we account for the optimal number of pilot signals, the degrees of freedom are actually the same. But now we are looking at the Grassmannian, so we don't need to restrict, our code books so that each entry is from one constellation. We can pick whatever set of points on the Grassmannian we want, right? Like just to see how better we can do, just compared to just taking products of quams on the coordinates. And so these are the results. So this is basically the SNR, and this is error rate on the y-axis, and this purple line is this pilot-based scheme, and this black line is one of our results, this union-bound optimization that I will show you in a minute. So we win by, I don't know, 3 decibels, which is quite a lot. This is from one of the older papers where they compared just some small specific constellations. So this is coming from numerical optimization, these black dots, and yeah, this is like some ad hoc construction in one very specific case. Okay, great. So we can try to distribute points on the Grassmannian and label them with bit strings and use that for sending data. How do we do that? How do we decode, first of all? So like the basic assumption is okay, our noise and channel matrix have these random normal complex distributions, and X is coming from from a fixed set of points on the Grassmannian, right? And remember, X was what we are sending. So these are these tall matrices. And yeah, maybe I should skip the proofs. These are complex normal, and when we condition on X, we have just combination of two normal distributions. So we can just write down the density function explicitly. And then you can notice that it has nice invariance properties. And then using those invariance properties, we can basically prove that when T is large enough, the distribution of X that would maximize this capacity is the uniform distribution on the Grassmannian. So this is like Shannon ergodic capacity. And the proof is really something which is quite standard for like standard technique in representation of Lie groups. You just kind of average, you take some arbitrary probability distribution, you average over the whole group, which way you obtain something invariant and it's uniform, and then you use something called Jensen inequality to see that, okay, by averaging I get something which transmits more information. So the capacity achieving distribution is uniformly distributed. For smaller T, the result is much harder and the distribution is quite non-trivial. And it basically shows us that we should really, I mean, a priori, X can be any complex matrix, right? But this result, this theorem, shows us that X really should be uniformly distributed on a Grassmannian, or rather finite approximation of uniform distribution on the Grassmannian. And hence, we can just imagine that X is already, represented by orthonormal basis. That it's just this tall matrix whose columns span the subspace, right? So how do we then decode? Well, with this maximum likelihood detector, we just look at each point in our constellation, and we will try to see which conditional probability is the highest, right? That's the maximum likelihood of detection. And again, we have like explicit formula for this, and now we can already assume that X is this tall unitary matrix, which simplifies this a lot, like this inverse can be get rid of and so on, and we end up with this guy, right? And remind that this is this orthogonal projector. Mm-hmm. But this is nothing but the chordal distance between 2 points on the same Grassmannian, right? Like this is the general formula for the chordal distance, just a norm induced by the Frobenius inner product. And when I'm on the Grassmannian, Yeah, sorry, I should have used x and y here. Yeah. Yeah, I just use these two properties again, and I get this very easily, right? So this maximum likelihood detector is maximizing this trace, which means it's minimizing the chordal distance, right? So it's almost like the thing that I showed you before. We are just minimizing the distance to the point. We are running through the whole codebook and looking at the minimal distance. That creates problem for the detection, but let's put it aside for now. And let's see at the problem of what is the optimal constellation given the size. Like if you want 16 points on the Grassmannian or 64 or 512, how do we get some nice constellation? Well, intuitively, the maximum likelihood detection is just looking for the closest point. So we should have these points as far away from each other as possible, right? So it's what we call chordal criterion. So we are looking at the minimal distance of these points. We are maximizing over all possible set of points, right? Which is, okay, so yeah, which seems reasonable, but actually when you try to prove it, it turns out that you can write down the probability of error of that misdetection. Let's say xi was sent and your maximum likelihood picks xj. What is the probability of error in this procedure? It turns out that there is a formula for that involving some residues, but you can massage it a little bit and write it in this integral form, which Mathematica isn't really able to handle very efficiently, or at least I was not able to handle it very efficiently. And here, what we have here is alpha, which is just some rescaled SNR. We have these principal angles, or rather the singular values. So the cosines of principal angles, and that's it. We have this variable theta, which we integrate over. The thing is that when rho is small, you can just use this expression to derive that the probability of error depends on the chordal distance, like this. So that kind of justifies this chordal distance criterion by maximizing the minimal chordal distance, we are minimizing the error. But for larger SNR, we have another asymptotics. We have this kind of product. So really what we should be looking at, because people want to send at higher SNRs, is this what we call coherence criterion. So this is this determinant thing, right? And you know, that's for like two specific points in your constellation. You can either take the minimum overall or soft minimum or maybe union bound. So we like a lot of this work was just trying which cost function works the best in terms of these error rates. So I will show just one of these algorithms. So this numerical optimization, like we are supposed to distribute, let's say, 64 points on the Grassmannian, right? So like naively written, we are optimizing over a product of 64 copies of Grassmannians, which is a huge space. So instead, what we do is like we always look at two closest points. We find the direction using Riemannian gradient. We find the direction in which when we move the fastest away from these two, from each other, and then we move some distance in this direction, and then we iterate. And there is some kind of line search procedure that dictates how far along this distance should we go, and that's what we did. Yeah, I forgot to show you this, but I can come back to that. So this is a set of random, sorry. Yeah. This is a set of random lines on Grassmannian of lines in the real space, just lines in 3D. And yeah, so here, for example, we have lines which have minimal chordal distance 0.26. I guess maybe the green and red one, right? And so what we do then is we run this optimization, and it increases, which is kind of visible here. The green and red are further apart, and the final minimal distance is much higher. And this mu is basically telling you how far along the direction we are going. So in the beginning we go some amount, and in the end we almost don't move. And this is how the optimization looks like. So there's always some kind of flip, and then we do better and better, and then there's some kind of flip. So maybe it's better to just run the animation. You can see what these iterations are doing. So it's just kind of sequentially moving the points, always finding the kind of the worst offending pair, and then trying to separate it.
I see. So it's like one at a time or two at a time.
Yeah. So later we did this also for the other cost functions, and we also implemented like a hybrid version where instead of looking at just two like pair of the most offending points, we look at, let's say, we find the most offending pair, and then we look at, let's say, L neighbors, and then we kind of average the direction among these L neighbors, right? Because when we are moving just 2 points from away from each other, there might be 3 points which is also very close, and by moving away and not taking it into consideration, we might be moving towards it, right? You know what I mean? Yeah. So we are trying to kind of average the direction so that this doesn't happen as often. So we have a lot of results like this. Yeah. Okay. And then there is the detection problem. So there is something called sphere detection. You can do some partitioning of your space and just look at examine the maximum likelihood in just some kind of big neighborhood and so on. But we wanted to do some ad hoc construction. It's so-called structured construction, kind of like this squam thing, right? Where you just use basically rounding to the nearest point on coordinate-wise, and that's it. So we invented this thing called grass lattice. So the idea is map a grid like Quam into the Grassmannian, but so that it's optimal with respect to one of our cost functions. So how does it work? We just first take this basically hypercube where we will construct the grid, and we map it through the inverse function for the distribution function of the normal distribution. And then we have this weird mapping z times f of norm of z, which maps it to the unit disk. And this makes it actually uniformly distributed in the unit disk. So this 1 and 2, what it does is it creates a uniform distribution on the unit disk from the hypercube, kind of explicitly. And moreover, these maps are easy to invert. And finally, when we have this unit disk, we can map to the Grassmannian just by adding this square root. Right? So this is like for just one antenna in this complex projective space. And this is how it looks like. On the left, you have these distributions, and on the right, you have the grid. Right. So this is this first mapping, and then the second mapping. So now we are looking at uniform distribution in the disk, and then in this case, the complex projective space is really just the usual sphere, and it creates this kind of distribution of points on the sphere. And we know that when we kind of put more grid points in the beginning, we will approach uniform distribution here. But as you can see, this is kind of using the determinant criterion, like this interpretation through determinant that we should be doing something which preserves the measure, preserves the uniformity of the distribution. So the distance is not really controlled here well, but you can just kind of cut off like a half and use this other chart, right? So before I map w to the square root, comma w, and now I do it the other way around. So I just, shrank the grid and put two of them there, and they overlapped in the corner, so you can just rotate one of these. So this kind of gives you a nice distribution of points on the sphere, or in general on the complex projective space. And you can easily invert this. And it's, it doesn't give you as good distribution of points as these numerical optimization techniques, but basically, you use these points as constellation points, and when you want to detect, you just, you measure on the receiver some point on the sphere, you run these maps in the inverse, and you obtain a point in the square, and then you do what you do for the Quantum constellation. So you can actually reuse the hardware or software routines, right? So that was the idea. And you can actually do some of these things also for the arbitrary number of antennas. The problem is that we don't really have. We have just like the last part, right? So we have a map from this domain in matrices. So this is the operator norm. So we have a nice map from this domain to the Grassmannian. We have the inverse map, which is also quite easy, but we have no way of kind of filling this domain nicely with grid points. So we have some ad hoc construction for m equal to 2, but the performance is not very good. Okay, and finally, this is a work in progress, where I actually hope to use Mathematica more because of its finite group capabilities. When you have a finite subgroup of your U of t, so this goes back to this description of the Grassmannian as U of t quotient by some subgroup, right?
Mm-hmm.
So if we have some finite subgroup of U of t, and we pick one point on the Grassmannian, we can consider the orbit of this point by this finite subgroup. But that gives us a some kind of constellation. And this base point actually matters. So here you can see the values of the cost function for random base points, and then the result of some preliminary numerical. So I just coded, few groups in Python arbitrarily and tried some Riemannian optimization. And the Riemannian optimization will give you these red lines. So I think this was the maximum minimum distance. And this is at random. So you can do much better than just, random base point. One way to get some intuition, imagine that your finite group is just a rotation by, let's say, a rotation of a ball by 30 degrees or by some number of degrees. So if you pick a base point near the equator, then the rotation will produce points which are quite far apart.
Mm-hmm.
If you pick a base point near the axis of the rotation, all these points will be very, very close together. So yeah, that's one way to look at it, like be as far away as you can from the fixed points.
So you want to use the group action to spread out a good constellation based on the base point?
Yeah, exactly. And there is also a possibility to efficiently decode. This is probably optimal base point for one specific group for CP1. Was found actually many years ago by a former colleague from Huawei, Jean-René Pital, who actually used Mathematica. He just took this small group and small space and wrote down the function and then let Mathematica optimize it, and he obtained this formula for the optimal base point. I just ran the numerical simulation, which is much better than much easier than doing like these k points, because you are optimizing not over the set of points. That's what the finite group takes care of. You are optimizing just the base points. You are really optimizing over the Grassmann manifold, and you don't have to do some special tricks. Another thing is that the cost functions are all invariant with respect to this ut, so in particular to a subgroup. So you can just look at the distance or the cost function with base point and something else in the orbit. So here it means that just evaluation of the cost function goes from quadratic complexity in the number of points to linear. And you can also simplify it, like for our specific cost functions, you can find some simplified formulas. So numerical optimization leads to like quick win compared to what we were doing before. And now I'll try to explain why it should have, so this is really work in progress, but why it should have efficient decoding. The thing is that when you have a finite group, which is abelian, which is commutative, when all its elements commute, what you can do is you can always find a realization of this group or like a set of coordinates so that this group is acting by basically diagonal matrices which has some exp on the diagonal, right? In other words, you are really looking at so-called Toro subgroup, and this is how it looks like. This is your base point, this is your group element, this is your group element squared, this is your group element cubed, and so on. So we are kind of, putting points like in this direction, but it's kind of on a torus, so it wraps up, right? From the 15 you go to 16 here, from 19 you go to 20 down here, and so on. So you have this lattice on a torus inside your Grassmannian, pretty much. And when you write down this maximum likelihood detection, you have these like cosine functions and so on. But you can when you replace these cosine functions just with polynomial approximations, instead of the true Voronoi region, which is shaded here, right? So this is like a zoom to the zero. You get this kind of Voronoi region, right? So what you can do is, okay, you have this group which is like this 1 and this 2. So you know that the lattice is spanned by this vector and this vector, and there's a very large angle between them. But now you can use this, how is it called? Lattice reduction technique, this LLL algorithm. There is an algorithm that, when you give it a lattice like this, discrete lattice of points, it will spit out a nice basis in terms of, okay, these basis vectors are all as orthogonal as possible, or,
Right. So here, generators 1 and 7 would provide a very nice basis for this.
Yes, exactly. And you can do this algorithmically, and you can kind of pre-compute this. I mean, these LLL type algorithms are kind of heavy, but this can be pre-computed. And so then instead of like the true Voronoi region, this hexagon, you would have this square. So there is some mismatch, there will be some error, but the decoding will be just, okay, run this, just transform to this pre-computed basis and do what we always do with Quam, just coordinate-wise rounding. Yeah. And this you can do for abelian groups, but pretty much all. I mean, the statement is you can find some nice groups with big abelian subgroups. So then you can kind of decompose the group into abelian part and cover and the rest, and you can cover the whole group with like translates of the abelian parts. You can kind of do it in steps. And so I coded some series of groups in Python, and there are some like general bounds, how many points you can put on the Grassmannian so that their minimal distance will be at least this or something like this, and this is the percentage of the bound that is attained. So these bounds are not sharp, and as you can see, when you go with the number of points, like with the size of the group to higher numbers, it deteriorates quite rapidly. For example, here or here you have just like 50% of the bound, but for some group you are still at like 90% of the known maybe non-tight bound, which seems to be quite good. So like there is a potential. Basically, what I'm working on is like algorithmic search in finite groups to fish for like nice examples that are as close to the general bounds as possible. Funny thing is that actually finite subgroups are not really classified. Once you fix T, it's classified only up to 4. Right? Because you can have like infinite series in each, and then arbitrary, like a priori you don't know which ones. And each finite group has this property, like if you fix dimension of your space, this T is this number of transmissions that you can do, then there is a number attached to that, which kind of restricts how big the abelian group can be. And this number is pretty high, but for big D, but I haven't seen it yet for small D. I mean, there is a paper, but it's behind the paywall. So that's one thing, like there is a hope, there are some structural results. And last thing I want to say, I actually started this finite group orbits with the hope of like, okay, we know that the capacity maximizing distribution is this uniform distribution. So let's approximate this uniform distribution on a group with finite subgroup, right? And then we pass to the quotient to the Grassmannian. The thing is that you can't really do that. There's this notion of group approximability. So you have a metric group in general with invariant distance function, and you say that it's epsilon approximable if there exists a finite subset with its own group law such that each point of the big group is at most epsilon from the subset. And when you take 2 arbitrary points of the subset, the original group law and this H group law are epsilon close, right? So you're not really asking for a subgroup which, so that all points from the group are at most epsilon away. We're asking for some subset which has very close group law with this property, right? And you say that group is approximable if it's epsilon approximable for any epsilon. So that was my hope. Like, if it was like this vague idea, if only UT was epsilon approximable, then I could just take this sequence of H's and do this, right? Turns out by a theorem by Alan Turing that if a Lie group is approximable, then it is compact and abelian. So it's just a torus. It's a product of U1s, basically.
Mm-hmm.
So that's a quite old result of his. He spent some time in Princeton, and it's a really nice short article, which is kind of self-contained. He mentions that this problem was suggested to him by von Neumann. It's yeah. So like my hope is blocked, but still, maybe at least for some specific cases, which for applications is good enough. Yeah, maybe there is something. Okay, that's where I will stop. Thank you.
Wow. That was a lot.
Yeah. And I didn't even talk about these P2P, about this other signaling than person to person.
Peer-to-peer, I guess.
Yeah. This was just P2P, then broadcast is whole another set of programs, and so on.
I mean, I'm
Yeah, so
familiar
there's
with Query, phase amplitude modulation. I know I go to tech shows. I've been to tech shows in Silicon Valley and see the eye diagrams for the oscilloscopes, the high end oscilloscopes. Oscilloscopes that cost $200,000 each or whatever, and they're showing all this modulation that they can do, and had very little idea of what types of error correction that goes into it, and this was very interesting to see the applications of complex Grassmannians to that.
Yeah. I mean, there are some applications of real Grassmannians as well, but it's usually in computer vision. Like when you want to represent, I don't know, like a rotation of shapes or something like that. It's I forgot. Like I know when I was looking, like curious what other Grassmannians appear in applied math. It was usually just the real ones. So it was quite nice and surprising to see complex Grassmannians, quite exotic.
Right, and
applied.
that's because we're dealing with signals that are encoded with complex numbers, with phase and amplitude of complex vectors.
So
yeah,
my
I'm wondering.
Was that
now I'm curious if this is applicable to quantum computation, dealing with qubits as those are encoded.
That's a great question. That's a great question. Unfortunately, so we had a project. So I was preparing another project in Huawei, this type of project where we wanted to tackle quantum computation because I have a friend at the University of Bologna and she does quantum groups and she's interested in quantum computation. And I knew that this is kind of close-ish, Unfortunately, this project was not funded. Like the strategy at Huawei shifted, so even though they were preliminarily very optimistic, then they kind of, But yeah, we really kind of wanted to go in this direction, but unfortunately, it was not funded. So I can't tell you. But yeah, there are definitely some intersections with quantum computing here or like quantum information theory.
Very cool. Pavel, James, do y'all have any questions or comments?
No, I just wanted to say thank you for that very in-depth, comprehensive presentation. That was quite impressive, just the sheer breadth and depth of that.
Yes, absolutely.
Thank you. There's a question in the chat whether the slides will be made available. I can just send them to you and you can send it to like regular participants or I don't know how to do that otherwise.
Sure. Yeah, you can send the slides to my email, and then I can forward those along.
Yeah, thank you. Yeah, that'd be great.
I'll stop sharing.
Great. What is the kind of like next in line for the research directions that you want to take? Not sure if you did mention in the presentation, but what are you looking forward to next?
You mean in this Grassmannian project or in general?
No, just for yourself. Like what are you going to be busy with next in terms of research?
So I started as differential geometer and then moved to representation theory, and then this kind of pulled me towards these like discrete structures or like discretizations of space that I was familiar with, like from other side. So I really wanted to explore that more. Like there are other. So this idea of using group orbits is like the straightforward one, but there are some other types of things that you can do to generate these discrete subsets or finite subsets that you can then maybe apply in these Grassmannian communications or just use them to capture some kind of geometry. Like that's so right now we were really looking at these distance properties, but you have things like discrete curvature and stuff like that. That's a whole another business that can be explored here. Like so that could be also interesting, right? look at the curvature that's results from these kind of group actions.
I'm wondering, Pavel, here what the potential connections are for inferogeometry.
Somehow I was triggered a bit by these epsilon representable groups because we are also getting some structure which would theoretically be somehow interpreted as some groups or something like that. Yeah, so this was kind of triggering a bit for me, but then it was kind of killed by this Turing's theorem, right? But anyway, it's kind of interesting. I just wanted to ask you, so these vectors, which are this vector which you are sending, the x, and the vector which you are receiving, the y, they cannot have arbitrary values, right? They are just even the values are discretized in every component in the matrices. They are like, if I understood it well, they are just yeah. So you are not really, they are not points like in. Is it like, can you also work with some discrete version of Grassmannian or something like this, or is it in lattice or something like this, or
So
is
what people do is people in this area, they also look at Grassmannians over finite fields. So maybe that's one way. That's really like a combinatorial model, right? So that's one way to approach it. I mean, and yes, I like in practice you are always looking at finite sets, right? Like the smooth or continuous is just like a convenient mathematical model, but yeah, in practice you are always looking at finite sets. Regarding the Turing's theorem, it was disappointing for me as well. But for example, I haven't looked. Maybe there is a hope of doing something like this, as I mentioned, with like other schemes. Like if groups don't work, maybe you can try groupoids, right? If groupoids don't work, maybe you can try some kind of association schemes and like more esoteric notions, right?
What we are actually trying to do in infrageometry. So basically, we are having this graph or hypergraph, which is being generated by some kind of elementary computations, and we are trying to somehow apply a similar method which you would apply if you observe the world using geometric methods. So you have a ruler, you have coordinates, you want to put some coordinates on it, and you are basically studying what is it describing, how does it transform, what are the natural structures which are appearing. So basically, it turns out in this setting you can also define some sort of observables, or like which are kind of represented by some bundles of chain of paths in the graph. You can also coordinatize by kind of like minimal path and so on. And we are basically hoping that we can make some framework where there is also going to be some natural structures appearing, like fiber bundles and maybe like principal fiber bundles. Maybe there's going to be some rules for which these coordinatizations are going to be producing some kind of groups in the fibers or something like this. So this is kind of what we are doing. So it's like a direction of like yeah. So it's not like discretizing, but kind of like asking if we can build similar language, if we can observe these complex systems, these complex networks using similar language as differential geometry. At least this is kind of, so I've been here a little over a month, so this is at least what I've understood so far. I hope this kind of corresponds to the like philosophy what we are trying to do. Yeah. And how could actually, if this precisely, I mean, definitely like complex Grassmannians, some discrete versions of this, it would be cool. These groups, approximation of the groups, that's a very interesting notion. Yeah.
But you have just like deterministic machines or
Well, this is actually something what Steven always mentions, that he would like to somehow add some randomness inside, which so far kind of I'm not adding any randomness so far. I'm just building the frameworks and kind of laying some groundwork regarding these coordinatizations and the structures which can come out of that. And
because
yeah.
we spent some time when we were looking at these interpolation problems and these like processes on Stiefel manifolds or this manifold of singular vectors. Like you formulate it in a smooth way, right? You have some kind of random process, but in practice you have like finite set of samples and you try to track them and do some kind of Kalman filtering and so on. So I'm just right now thinking if maybe you can just turn it on its head and then say, okay, if I take these like maybe think of a heat kernel expansion, right? So that gives you like time dissipation in your space. Can you maybe discretize this and start with like functions from the heat kernel expansion and just sample points, like simulating like diffusion in this way? Will it produce the same kind of space? Like probably not topologically, right? Because I don't see a reason why like a long-term flow would kind of wrap up topologically. Maybe, yeah, I don't know. But maybe locally it could reproduce some kind of geometry, right? I mean, it's hard to say. I don't recall if these heat kernels are kind of like if you can have two Riemannian manifolds which have the same heat kernel invariance.
There was some hope that this is like the full invariant, right, of Riemannian manifold, some kind of what I'm not sure about it.
Yeah. So yeah, maybe that could be also kind of fun experiment.
That is definitely kind of infrageometric direction.
Yeah. Okay. Yeah. It's kind of I'm kind of hopeful with these local approaches because we run into a wall precisely with like global geometry. The problem was that all these manifolds are compact. So when you are not sampling in short enough times, you kind of wrap around the whole manifold, and then there is like a big holonomy that kills you, and you don't really know where you are. Kind of, if it makes sense. If you take too big of a step, you don't know where you will end up somehow. But as far as I understand it, you try to build the spaces like locally, or you are hoping also for like global topological results, or like if you do this kind of.
Well, so what I'm trying to do now precisely is basically somehow define these coordinatizations and basically do some local analysis on them, let's say, and then maybe we are running some experiments, like we can specify some set of rules, and we can basically do it. We have efficient algorithms which can generate all possible ways in which it can transform the hypergraph. You are kind of trying to think what would be the correct notion of observer, what would be the correct notion of some coordinates on that, and seeing because basically how you imagine the structure you imagine as something that we are some kind of like we are basically observers which are having the similar methods, hence we are going to be observing somehow similar structure. So it's not like the structure is here not postulated, the structure is here kind of like coordinate dependent. We need to have the observer to get some structure, and then we can consider similar observers and check what is the structure doing. So currently is at the stage, for instance, that I'm building these coordinatizations. I'm now defining some version of calculus basically on directed graphs, which you can then extend like to these grids of directed graphs. I have also in mind some experiment regarding like, because there is in the discrete world we are dealing with ambiguity, and I think this whole kind of this Wolfram project is also based on basically dealing with ambiguity and somehow trying to interpret the ambiguity and keeping track of that in some ways. So basically, for instance, in the coordinates, there is going to be some ambiguity. Question is how to deal with that. You can, for instance, group the points which are having the same coordinates. You can consider them as some kind of fiber, but some kind of fiber. You can consider as a fiber bundle. You can define connection on that. You can maybe think if this in some limit if it's gonna really converge to some geometric structure or geometrically describable structure or not. So this is kind of what we are trying to. The problem is we are not having much framework. This is kind of like we need to kind of build the mathematical framework basically for this from scratch. But it's kind of seems like a natural thing to do because kind of people have observed, and came up with manifolds, for instance, right? They have real analysis. They came up with manifolds, so we should be able to kind of come up with some similar observables for these complex networks and try to somehow get some geometry on that. Yeah.
Right. So do you have some do you take some input from discrete differential geometry or?
Yeah, so I'm also kind of like reading around, and there are various directions. There are like so people are. I mean, you can either like discretize stuff. You can always ask, what information shall I store on the graph? We have hypergraphs, so like NRA relations. What can I store to kind of approximate the space somehow? If you take like on Riemannian manifold, like epsilon neighborhood graph, you are kind of for epsilon small enough, you are storing topology. If you take like geodesic segments and metric, then you are also storing like the metric graph, and the shortest paths are going to approximate geodesics. You can, of course, ask what's going to happen with the Dram complex. Can I define some, let's say, discrete Dram complex? Discrete Dram isn't going to be quasi-isomorphic to the original one. So there are like multiple questions regarding discretizations, which are not like fully, or connection. For instance, currently, Stephen Wolfram is very much interested in like connection or stuff like that. And so it's even like question how to discretize connections and stuff like that. And yeah, so this is one direction. There is another direction. Which is like you would have natural. You would take one hypergraph, and you would try to like one abstract simplicial complex, which is kind of simplicial complex, right? You are having like the nerve. You are having this clique complex and stuff like that, and you can define some natural notions for that. There are mathematicians who are trying to like design like geometry on abstract simplicial complexes, just kind of like discrete versions of geometric theorem. But we are kind of doing something different. We are kind of doing something like we are having some chunks of computational space, and we are trying to somehow parameterize them somehow. So it's something in between, but I think there are like inputs from all sides, what can be done and what could make sense, and actually how to interpret stuff. Yeah. And
So
what
two
is there?
things. Sorry, if I may, just two things. I don't know if you know, but Braňo Jurčo, you know Braňo, right? Yeah. So he has a PhD student who's like doing geometry on simplicial complexes.
Cool.
Fancy job. Yeah.
That's very interesting. I will probably meet in CERNI in January.
I'm not quite sure. I think he kind of extended too much his PhD study. Like he's no longer funded, so I'm not sure if he's coming. So
we're still on the live stream, so I'm gonna jump off now. But maybe you guys can turn the stream off and you can carry on chatting. But
maybe
enjoy the weekend, guys.
He should have answered some more questions actually. See you. Thank you.
Yeah.
Yeah. So actually, what is missing, I think, in this infrageometry is usually some kind of framework. This is what I'm kind of trying to build now, and there is some stochastics. What is definitely missing? Some kind of yeah.
Well, with stochastics comes into play on how the hypergraphs are generated. Like, for instance, where a rewriting rule will apply if it applies to multiple places at a given moment. But yeah, so and then also stochastic or non-global features would be like, dimension should be defined locally, because in some of these hypergraphs, they're very exotic discretized spaces, and the dimensionality per location would vary. Sometimes it's very wispy and sort of linear, and then that would evolve to some 2 or 3-dimensional spaces, and then in between you might have fractional dimensions, or there might be fractal structures giving non-integer Hausdorff dimensionality at particular places. So it's like, can you still define some notion of a tangent space at a point, even if there's a fractional dimension at that point? Or
because you see basically
to parallel transport.
Because what is natural for manifolds, if you are observing like space about which you think that it's kind of like a smooth manifold or whatever, then these model spaces, right? You have model space R to the power of D. This does not exist here. We are not having like model space. Yeah, and basically everything in the manifold here in the geometry is fixed by this requirement that you have a model space. This also fixes the dimension and stuff like that. It turns out in this discrete world, when we are describing the computational universe, we are actually not having this model space RD. We might have maximally some model rules, which are kind of some special rules which are generating space, which are gonna have similar properties to what we would consider to be RD. Yeah, so which, for instance, is gonna have this growth of the volume balls, the rate which corresponds to like integer dimension or something like this, which is gonna which is gonna generate, like let's say which is gonna have no Betty numbers and stuff like that, and we can say this is our model generating rules, but we are not having like fixed model space. So if you kind of glue it together, let it act on some hypergraph, actually the dimension may be fractional. The dimension is like not something what you fix, it can, and the natural notion here is like the growth of the volume ball, which is again something to make some experiment on. Maybe one can even do some a little bit more clarify that how much it mixes, for instance, with this curvature, right? Yeah, so this is like one invariant basically, which is natural in the discrete world, in this thing, and of course it can be fractional. I mean, there is no reason why it should not be fractional if you are just computing kind of like growth rate of the geodesic ball. Yeah. So
yeah, these fractional dimensions, they sound I don't know, like usually you don't do like smooth calculus of any kind over fractional spaces. So that's kind of yeah.
I mean, the calculus comes in when you do coordinatization. You coordinatize, you have like a tube. The tube you have put some direction because you need like oriented reline, right? It becomes like directed graph, and on this directed graph you can actually integrate and you can actually take derivation. Yeah? It's like a discrete version of that, and so this is what I meant when I was saying like doing analysis. So this kind of analysis you can do here. You can put like some perpendicular lines, perpendicular bundles, and then you can coordinatize your.
So it's like algebraic definition on let's say a billion groups of some objects. Like
probably, yes.
When you define connection, not like with Christoffel symbols, but as an abstract operation on.
Yes.
Yeah.
Yes. So connection, for instance, how I would imagine here, connection would be that let's say some points, because there is this ambiguity in this computation of the coordinate. Some points actually are going to have the same coordinate because there is going to be like, if you compute coordinate, you are taking the shortest path, right? But if it's discrete, there is multiple shortest paths and multiple points can have the same coordinate. So this would be like represent some kind of like a tangent space, let's say, yeah. And basically the paths would be some infinitesimal paths or whatever. And basically on the boundary of this tangent space, you would have one at the point with one coordinate, one ball, one subgraph at one coordinate, another subgraph at the other coordinate. Yeah? Then you would have some edges which would connect this stuff. Yeah? Choice of a gauge would correspond to choosing like the one which is lying in the base space, you know, and all the other edges would be considered as kind of connecting two fibers. And basically a connection would be choice of a lift of this or like choice of one of these guys. You can,
Yeah.
for instance, I also have this plan that I would like to, you can then kind of enumerate like loops or something. You can maybe think about some kind of quantum field theory using the Wilson loops or something like this. You can try to associate some numbers to the loops like holonomies. I think that there is some theorem which is telling you if you have some collection of loops, if it actually if you have some of these Wilson loops of these traces of holonomies, if it represents a gauge potential, if it represents the connection. Yeah. So there are some set of conditions which have to be satisfied so that these traces of holonomies they represent a connection. So I was thinking maybe I can somehow also make experiment, like try to enumerate it, try to see how far is it, or if there's some chance that it satisfies some relations. Just experiments like this. But I think this is at least my idea of connection at the current point. Yeah.
Okay. So when you say connection, I should always imagine something like a principal connection or
Yes,
Harris one.
yeah. This is how I also imagine it. Yeah. So
So Pavel, may I ask a question? You mentioned ambiguity about the coordinate. Can you clarify what you meant?
yeah. So for instance, if you are having, let's say, imagine like a grid, just a discrete grid, right? And you can then kind of add additional vertices somewhere. We can kind of thicken the grid. You can decide, okay, let's add like a additional edges and additional vertices at nodes of the grid. Yeah. Then basically, if you have this point at coordinate 2, 3, which means that there is like shortest path of length 2 and shortest path of length 3, you know, then basically if you build on the top of that some other points, all of these points, they are going to have the same coordinate because they are going to have the same distances to this. Yeah. So basically these all these points which are going to be kind of glued to this node, they are going to have the same coordinate. So you can imagine it as something what is like some subgeometric structure that the observer who is kind of like measuring these two coordinates, he does not see it, but there is some internal structure which I would say, okay, it's fiber, it's some kind of fiber. Let's work with that. Yeah.
Okay. I'm wondering if the concept of a fuzzy set membership might be helpful.
I don't know that concept. I don't know that concept.
Oh, okay. Yeah, there's a concept where we define a membership function to a set. In usual set theory, we have crisp membership, as it's called. Either it's a member of the set or not a member of set. But if we can define non-step function like membership, then we can define membership in a fuzzy sort of way. I'm just wondering whether that might be any helpful for this.
Could be a cool notion to formalize actually some phenomena happening here, because we are not having only one hypergraph, and this is, for instance, not yet fully explored. Like we should actually think we are having this rewriting system, right? This rewriting system has more structure. This has like all this multi-way structure, and we are picking this one path, and you can kind of somehow take some isomorphisms, the different versions of kind of identifying these paths together, and these different kind of multiverses together, and there is definitely some space. Like Steven is hoping this is some kind of quantum phenomena that are basically hidden, and so on. So definitely like notions, some fuzzy notions that something is some half here, half there. sound actually definitely like interesting. Yeah, to kind of thank you very much. I will check it out if
Okay,
this
you're
is
welcome.
something what we could apply here.
Yeah, thank you.
For me, it vaguely reminds me of this notion of like path groupoid, right? Where you, of course,
Pa-
you have the topological space, and then you take all the paths, and that kind of creates your groupoid space, which sits above. It's like a generalization of fundamental group.
Mhm.
So it's like
This is
a fundamental group, but for non-closed paths. You just concatenating paths together,
Yeah.
and then it's a groupoid, I guess, because what do you lose in a groupoid from a group? You know, you don't
No,
necessarily
you
have
don't
a
lose anything.
defined.
On the contrary,
What's that?
like groupoid is richer somehow.
Mhm.
Uh,
But you're
Like
not
in
necessarily
group, in
having the
this
ability
unit
to
element,
concatenate any two paths in the set, right? So you don't have
right?
a completely defined
Yeah.
group operation.
In general, no. Yeah, that's true.
Mhm.
Well, it kind of depends on the definition, but when we are talking about path groupoids, when your space is not path connected, then yeah, you can't really concatenate paths from different. Like there is some compatibility. Yeah.
I think when we have a groupoid, like in the difference between classical mechanics and quantum mechanics, in the atomic electron structure, when the electron in classical mechanics would radiate radiation continuously, but in quantum mechanics it's discrete, and there's this Rydberg combination principle where only certain frequencies in the spectrum can be added to get another spectrum, but not all of them. I think that's where this matrix mechanics started, this quantum mechanics started. So that those frequencies, I think, make up a groupoid instead of a group. So I'm thinking maybe it implies some sort of non-commutativity when we have a groupoid. Is that correct? At least in the quantum mechanics, in the Ritz-Rydberg combination principle, in the hydrogen spectrum, for example, I think that's true. But I wonder if that's a general thing.
This groupoid, you can also kind of like dual picture. You can imagine kind of that one hyper edge means like some place which you can kind of reach in. If it's like an edge, right? If it has n vertices, you can imagine this is a place which you can reach kind of in n ways. So you can kind of also kind of maybe build some kind of like imagine that you have in terms of the dual sense that you have kind of actually paths from there are kind of different paths flowing like between the hyper edges over the edges or something like this. So I mean there's definitely like if you consider connectivity of the graph, then you can build path groupoid from that, right? I mean this is a structure which exists there, right? I mean, it's just a collection of all paths, basically.
So going back to, I think, Dugan's question earlier, what exactly are we missing in a groupoid from a group?
It's really just that the composition operation is only partial. You can't really
So,
compose
yeah.
arbitrary.
Yeah. So Paul, uh, can you repeat what you said? It was not. I didn't quite catch.
I mean, mm, um, wait, yeah, so wait. No, that I would say that there is, how do you get path groupoid from a topological space? there is definitely like if you pick this is wait so I mean like this you can consider like there is this there is this fundamental groupoid, right? Also there is fundamental groupoid. Fundamental groupoid is what it is. It is
Just the
it
space of set of all paths in the space.
is the set of all paths. So a fundamental groupoid. So how would we get now? And you were saying some kind of less than groupoid. So you were saying path. What were you saying? Vit Tuček.
No, I was thinking about fundamental groupoid. Like when you said that
Yeah.
you have like multiple paths going to the points, this is kind of like
Yeah. So you have path
that's
groupoid.
yeah, that's really like what you see in the topology, like
Yeah.
very simple way.
Yeah. And you can maybe see it here, like either like in the on the edges or something, or if you want to kind of involve hyper edges, you can either define like path which kind of go through hyper edges, through the edges, right? Or you can also see it that like dually, like that like basically put like a middle point in every hyper edge, and you can imagine that basically the number of edges is all possible paths to the other. So you have some kind of multiple notions probably of how you can associate some kind of groupoid, path groupoid to a hypergraph.
Right. I mean, you could just put clicks, you know, fully connect each hyperedge with edges.
Mm.
Just assume that you can go from any one point in a hyperedge to any other point.
Yeah.
If it's undirected. If it's directed, then you have to decide like which,
Yeah.
what the directionality is for the vertices of a hyperedge.
And I think that Xerxes has some paper where he is actually trying to somehow well, I did not read it, but I think he's somehow interpreting the rewriting rules as some kind of homotopies between the paths, right? In a way, I don't know. Dugan, did you see it, or did you read it, or you also don't know what was the but something like that, right? He's considering like he wants to consider some rewriting rules as homotopies between the paths, and he has this claim that there is some object which you associate to the rewriting system, some infinity groupoid that you can associate to a writing system or something. This is just some pure homotopic kind of, because the first thing what I was thinking about, okay, so what can I do with this? I was also at the beginning, I just kind of started playing with Mathematica and with all this stuff. So I implemented like simplicial sets and so on. And I was thinking, okay, maybe I can take like homotopic limit of like the rewriting system or something like this, something discretize this telescope construction or whatever, and somehow start thinking about it. But I think we should actually maybe here like really take like path that maybe I would try to kind of really try to understand how to even like formulate, for instance, differential equation on such a kind of structure. What does it mean motion? What does it mean? Because basically people realized in the world that there are somehow some processes which kind of depend on infinitesimal change. Which what does it even would kind of such statement mean? What would such statement mean in this computational universe? And if we can, and I think Steven's goal would be basically to have some kind of that we could at some point say that some evolution of some rewriting system is basically converging to some discretization of some solution of some of like Einstein equation, let's say, So he would like to see like not the direction that you formulate analytically Einstein equation or Navier-Stokes equation or something. You formulate it analytically, you compute, you do ND solve or something, you compute solution, right? And then you discretize it. You can kind of somehow discretize the space-time and so on. But it would be, and maybe observe some phenomena on this. I think Jonathan Goddard was at some point studying some merging of black holes, right? So, and if you could kind of get some phenomenon like this, purely purely from the computer, from observing the computational universe, and not by going to analysis, formulating equation, computing solution, discretizing. If you can go kind of the other way, or somehow observe some similar phenomena as differential equations. So, for instance, my question is, what's motion on these hypergraphs, and can you actually formulate some? Because actually, why people started using like real numbers and stuff like that, right? Because they wanted to have some field where they can have actually least upper bounds, they can divide, and so they can have like derivatives inside. So because in like real numbers you can have both numbers and both functions and their derivatives. Because you can actually divide by scale, right? You can take the limit as scale goes to 0. So you have kind of real numbers give you some space where you can compare this stuff, and you can immediately, wow, I can formulate differential equation. Yeah. And now what can you do something? Does something similar make sense in this on like the discrete space on this kind of complex network? Does it make sense, and could it potentially lead to some actually the solution here would probably mean like you have some it would be probably in the end it would lead to some kind of classification of some interesting phenomena for some specific sets of rewriting rules, right? But you would like to kind of be able to describe them. You would like to say, hey, if I pick these rewriting rules, I'm gonna get and look at these observables, I'm gonna get like something what looks like merging of black holes or something like this. So yeah. I mean, this would be like probably a crazy task. This is probably not even like approachable, like theorem, like there exists a set of rules, and there exists a seed hypergraph such that when you let it evolve, you are gonna get discretization of Einstein equations. So you are gonna get something which is gonna approximate Einstein equations. Yeah, this is probably too big task. I don't even know how this could be tackled. But
Yeah,
actually,
well, I mean,
it's
like a
I
rewriting
don't.
rule like that to simulate, updates of a gravitational system, you would need the rule to recognize like how the space is being pulled, and then like update the space to reflect that,
Mhm.
and update the
Mhm.
space to reflect the motion of massive objects through it.
Mhm.
So it has to be like somehow aware of the local space-time curvature forces, and then update appropriately.
I think what also recently Steven was kind of open to was like working on some mesoscale, like that we are not going to be just considering pure hypergraphs, that we can also kind of attach to them some structures. Let's say we consider just function on nodes, or we consider some maybe like sheaves on hypergraphs in the more general case. Maybe it would be even kind of like if we could formulate some kind of problem like this, and it would if we could formulate something interesting for this kind of objects, and then basically you would have to explain, okay, so, but you can always explain it. You can explain what does it mean when I wrote like 5 on this node. You can say, it actually means that there is, if you zoom in, if you increase the scale, it actually represents some like that on the node there is 5 loops, and that basically you can then try to design some rewriting rules which are doing you see from 5 loops to 3 loops or something like that. So just kind of like purely discrete way to differential equation to interesting kind of solutions. This is what I understand. This is kind of what is my current philosophy, and what I'm kind of trying to develop, or to somehow see if there is something. If there is something, it's not going to be. I mean, to prove something, like really formulate mathematical theorem and prove something. I think this is not at all at this stage. Yeah? This is more like explorative, trying to define interesting notions, see what one can do with it. Yeah.
Yeah.
And define this framework. Define the framework.
Proofs and theorems are not the primary goal. It's just, given a discretized graph or hypergraph, how can you know what kind of space you're living in if you know at least a little bit of part of your local neighborhood. You know, if you're on a sphere, let's say, but you don't know that yet, you know, how can you detect that you're in a parabolic section of positive curvature given a little piece of this graph that you're surrounded in? Or how can you detect that you're a part of a flat graph? Computationally. Yeah. How can you write a subroutine to like explore around you and then deduce?
So if you are looking for examples, I would, in your place, I would start looking at this discrete geometry stuff. I mean, there is this guy, Keenan Crane at Carnegie Mellon. He does discrete geometry, and he also does like this kind of applied 3D geometry, you know, like different equations on surfaces and stuff like that.
I interacted with him maybe a decade ago when we were both grad students. And yeah, so he does a lot of. I've recommended to Pavel to look into his stuff, and you know, it's a lot of discretized two manifolds embedded in three-dimensional space. And so there, it's like, oh, you can take advantage of, you know, normal vectors and then sort of angles, dihedral angles between adjacent polygons on a surface to sort of get discrete notions of curvature and things like that. I think for and that's mostly what he does for the purpose of like computer graphics and computational geometry in 3 dimensions. But
I think
it's like, yeah, there's a lot of taking advantage of extrinsically defined curvature, and it's interesting to try to think about how you would define intrinsic curvature for discrete graphs.
Yeah, so that's of course the question, what is infra geometry? So you can also think, okay, so what we want, like without embedding, without any information, because kind of, for instance, if you look at the graphics of the Wolfram Physics project, some of the graphics, they are kind of motivational graphics. They basically used some in Wolfram language. There is some algorithm implemented. I think it's spring electric embedding and its variants.
Yeah,
which is somehow placing vertices and edges in some optimal way, which kind of people, again, mathematicians were thinking probably under some conditions how to put them together. Maybe Dugan knows more about it. I just kind of know that it exists and that it basically minimizes some potential. Yeah, that you formulate some potential, minimize potential, and it gives you, like, for instance, you want to repulse some nodes or something. Yeah?
right. You want different parts of the graph not to interfere with each other. So basically, you set all the vertices of the graph to repel each other electrostatically as a model, and then you want vertices that are nearby each other to stay near to each other. So the edges are modeled as springs that pull the thing tight. So you have a balance of forces, a repulsive force, and then a local edgewise spring force, and then the solution to that, you just kind of let it play out in a dimensional space, 2 or 3 dimensions typically. Although it's arbitrary what dimension you want to calculate that in, and then eventually there'll be an equilibrium point where kind of all the forces get balanced, and then you use that to visualize the graph, and it sort of typically it comes out pretty nice.
And I think that the next thing, what kind of, you have this embedding of these points, and then they are basically taking some, like, not fully convex hull, because it would be like one big ball, but take some kind of like locally convex hull or something, which they kind of fill it into some discrete surface, and this is what they this is what are the pictures in the Wolfram Physics project, right? So these are some kind of motivating pictures. I think this might not be necessarily what is kind of the infrageometry doing. Right, but you can also think, I mean, it's definitely interesting question. How does this embedding algorithm, how does it interplay? What kind of geometry does it generate? I mean, this embedding algorithms is also something interesting, right? But I think we are trying to like build some really intrinsic way of observing.
Yeah, so the reason I mentioned Keenan Crane is that I vaguely remember, I might be wrong, that he was using this discrete geometry stuff to really like solve some geometrical equations on these surfaces, like the heat equation, for example. And so
yeah,
like
and
my
conformal
idea would be
coordinatization.
Yeah. So like look at it closely and see if you can like extract the like purely discrete stuff that's going on here, like without any references or like quoting out the references to the ambient space, right?
That's
Because he
definitely.
really works with a mesh, then he does some kind of like discrete Deram stuff and then discrete exterior calculus. And in like his ultimate goal is okay, I have, I don't know, numerically stable, nice, fast solution to like whatever heat equation on surface, or I don't know, on the Laplace equation on surface. But maybe there can be a hint, how to like what's really going on, like on these discrete objects.
Definitely, I will check it out. Thank you.
And
Yeah, but
in the worst case, there will be nothing, and you will just see lots of pretty pictures and animations. So
no, but somehow recently because I realized I wanted to get some kind of like visual examples of connection, just in the standard case. I realized actually Wolfram is even in the function repository. There is missing anything which would compute like a connection on a discretized embedded surface. I did not find any function for that. Maybe there are some third party packlets. Maybe somebody wrote some discrete geometry packlet or somewhere, but it's kind of also instructive for me to do it myself. So I was also thinking just to have some example, at least like what is like, how would you, and this is also interesting because kind of where would you like, this faces, right? Where do you compute it? What do you take? This is also interesting how to, I mean, eventually you kind of remember the rotation angles, right? And on the edges and stuff like that. Yeah. But it's not actually the only thing what this infrared geometry is doing. So it's just really purely like coordinatizing the graph and studying how does it behave under the writing rules, and if you can formulate infinitesimal concepts like motion, if you can somehow formulate some solutions of equations. But another one, there is this multi-way system, right? It's basically the rewriting system, and there you can ask like what is governing these transformations and so there's also like a whole bunch of people working with confluence, right? Confluence is basically that you would say your space is having some properties at some point. Then basically you evolve it in different ways. And it has at the beginning maybe it has different properties, but maybe all if you then evolve further and further, then all the possible branches, basically the property it's actually gonna kind of converge together. Or if you have some kind of aggregated property, it's gonna kind of converge together. Yeah. So there will be some kind of approximate kind of confluence. And if you do it like really on this microscopic simple graphs, people are trying to formulate algebraic equations using confluence that they identify basically they identify hypergraphs with matrices or hypermatrices and so on, and try to kind of use this confluence. I was kind of trying at some point. I was because when I actually first came to contact with this stuff was last year in Wolfram Winter School, and there I was kind of tasked like to do some Hamiltonian formalism for hypergraph rewriting, or just study if there is some kind of like notion of Lie bracket and stuff like that. So somehow I was then given this, that there's this insertion Lie bracket on graphs. So I kind of generalized it to insertion Lie bracket on hypergraphs and started thinking about there are actually some funny questions because if you have Lie bracket, you are having Poisson bracket, right? You take like the space of formal functions and you can do like we have Poisson bracket. So you could actually compute like the Poisson bracket of the number of vectors or the number of nodes and the number of edges. in a graph. I don't know what it is. It's non-zero. It's kind of proven by experiment is non-zero, but it's some combinatorial fun. But kind of I did not find the motivation and the and the kind of like the to actually compute it, try to prove what it is. Yeah. But and one can think again. Can one do some? This was the question. Can one do some Hamiltonian mechanics, or would it be some even like it would like the concept of cotangent bundle make sense, or some kind of construction on this, which would kind of. But for this, you need to first understand somehow a bit this the dynamics or what it would even mean, you know. And so yeah. So basically, this is kind of there's a lot of ideas what one could kind of build. Only thing it's kind of hard because the framework is kind of missing, but it's kind of I think that there is definitely like concrete steps. I think now I'm doing some concrete step actually to do there something. So
Did
yeah.
you try to take a look whether there is like a Butler and Minkowski algebra on these hypergraphs?
Why should we? I mean, of course, I have like also different, like more kind of like the down to earth like ideas, like things what you could kind of prove, right? Uh, but like I mean, this would be normal like some I would having some ideas like doing like this because people are doing this random walks on the graphs and computing like computing the amplitudes and maybe for Feynman integrals doing discrete Chern-Simons theory. I wanted to do discrete Chern-Simons theory on a graph and stuff like this. But why would you think that Butler and Minkowski? You mean like from like this surgery interpretation, like putting together some stuff, or that you would have some hypergraph operations. We would have some hypergraph operations, and they would kind of represent Butler and Minkowski algebra. Or
Just like a vague memory that I took this course by Martin Marko, and I vaguely remember there are these BV algebra structures when you have these like insertion brackets. I was
yes,
looking at this
yes,
operatic business with Martin Rubek and
yes,
so on. So
yes,
like
yes. That's actually a very
we are
cool
composing operats
comment.
and yeah.
That's actually a very cool comment because there should be something. Because the kind of the BV algebra I know is this BV algebra in this open string field theory or whatever. This is basically
Yeah,
constructed by
that's like a very important example, but there is like
yes.
an axiomatization. You have these kind of operations, they satisfy these axioms and so on.
Mhm.
And yeah, when I briefly looked at your talk here, it really reminded me of this like operatic business. And, a lot of these operations are on some level formally similar, right? Just and these are, I think you probably might specialize what you have done if you just look at the just the regular normal graphs with edges or maybe directed edges that would correspond to this operatic stuff.
That's actually a pretty cool idea. This is definitely something what one can have a look, and
So,
it seems like there's going to be something.
that will kind of allow you to view it as a computation in completely like different way, right?
Yes.
Like, these are inputs, some of these are outputs. Yeah, maybe one other way back to the geometry. When I was talking about this heat kernel and then maybe like trying to use stochastic rules to evolve the discrete structure. Maybe one place to look at would be this. There is this approach to curvature through probability theory by Cedric Villani. He got Fields Medal for some work
He got
on some.
Fields Medal. I actually saw him live. He was invited to Augsburg, I think, when I was PhD student there.
So he worked on some hard PDEs, but he has this nice book about like optimal how to, if I remember correctly, like how to get a Ricci curvature from like optimal transport. Like he invented I'm not sure if it was him, but like I of it because of him that there is a way to get at least some curvature, like maybe Ricci, just from measurable space, right? Like you don't need smooth space or a Riemannian structure. You can get some kind of curvature just looking at the measures. So maybe that's another like direction to explore. It's the stochastic stuff.
Cool.
Edric,
It's
is that the
actually
one
cool.
with the bow tie and very dapper looking?
Yeah.
The
Yeah,
spider,
yeah, very good.
bow tie and the spider. Yeah.
Mhm.
So regarding Pavel's question earlier about how to introduce this concept of infinitesimal in this discrete system,
Mhm.
I just want to briefly do a little brainstorm. This I've been reading this book on space and time by
Mhm.
Alain Conn et al. And there's a chapter by Alain Conn, chapter 4, which is called on the fine structure of space-time. And here he talks about the infinitesimal, right? When we talk about an operator, it's some in some sense a size. In a certain sense, its size can be like an infinitesimal. It can be smaller than any real number.
Oh, like
But
you're talking about like
zero.
surreal numbers?
Maybe it's related, but is maybe it's related. Yeah, is not exactly talking about serial numbers, but maybe it's related. Yeah, but yeah, it just triggered a thought just because in a discrete system we might have some operator or something and whose size in a certain sense might be smaller than any real number, but above zero. So yeah, just a thought.
So okay. So you are thinking like introducing some operators and defining like the notion of
Yeah,
infinitesimality in. Uh-huh. That could definitely also be. Yeah.
yeah.
What I was thinking, maybe at the very beginning, I had this idea of like, okay, let's really do like manifolds. Like let's really like tell, okay, we are not having RD, we are having space generating rules or whatever, and like we would have to, but somehow also you have to introduce some scale or something. You would have to we would want to define what does it mean for a function between like two discretized lines, right? Just it goes like from one line to another. Maybe you can remember some starting point or something, and you would have to you would want to kind of define what does it mean. Or it would not be just even function. It would probably be some sequence of function for every kind of scale or something like this. And I was just thinking if there is maybe some notion like invariance, that it would be kind of covariant on this space generating rules or something like this, that there's like subdivision, right? You are kind of just, but I didn't come far away. It was just kind of original. I was thinking, okay, maybe, but I cannot get over this scale issue or how this should be interpreted and stuff like that. Yeah.
Yeah, maybe when we go to different scales, maybe the limit, like the fractal dimension or something.
Mhm. Actually, what is also cool because I mean, of course, I mean, there is in this language there is natural scaling, right? Because you are kind of it's a natural notion because you are kind of grouping together things which have some same property, and at some point you can just group them. Okay, this is just one point. This is one point, and if there exists a path, I connect. But you can always kind of blow up to the microstructure, right? You can kind of always ask, okay, I'm having these 2 points. They are representing something, and I can blow them up to the microstructure, to some subgraphs or something like this, and yeah, and yeah. So I was thinking if there is not some notion like some compatibilities, like you have space generating rules and start with that like purely formally defining something. Yeah, but I kind of I did not find that some kind of like way how to handle it somehow. But I mean, like there are concrete project, for instance, all this. When I talk about this with like people from my surroundings, which are symplectic topology, symplectic geometers, then it's also like, does there exist actually discrete symplectic geometry? You know, and actually nobody knows. Yeah, nobody knows if there is discrete symplectic geometry. This is it should not be that hard because basically what is doing symplectic geometry, it is kind of like counting on a surface. It is somehow counting like oriented area, right? It is something. The symplectic form is somehow counting the oriented area of if you and what is there? Can you somehow discretize this notion in some other way? But maybe this is the
Simplistic. I mean, I
Yeah.
thought that
So-
meant that there was some operation on the tangent bundle that was somewhat complex-like. Was analogous to complex
Mhm.
multiplication.
discrete complex geometry. I also search actually like such buzzwords like discrete complex geometry also does not exist, basically.
Mhm.
But this
Well,
is like
actually-
not this is not pure like infrageometry, because Stephen kind of is not like into this kind of stuff. He's not like into constructing something or doing some kind of like he's more like he really wants to kind of understand this the description of the computational universe, I think. Yeah, he kind of really wants to kind of like see this see. I mean, he would be. I think that for him, I don't know. Now, Dugan tell me. I don't know him that much, but I think for him, like this, what I was saying, this
Yeah, he wants
merger of the
grounded
black
up
holes or something.
computational tools that can be
Yeah.
applied to arbitrary graphs, and
Yes.
then if there are patterns there, then you can develop theory based on that. But to
Yes.
and the goal is sort of differential geometry type of constructions, but hopefully to get computational tools that will allow for that in some sort of limit. But I guess he's not a fan of working backwards to take a manifold and then discretize it.
Is he?
know.
I don't think that he's. When I was talking him about proposing him some different, he's kind of, for instance, the Oliver Nil stuff.
Yeah.
Who is basically Oliver Nil. This is, I think he's at Harvard or something like this. He's taking like abstract simplicial complex, like the clique complex of a graph,
Mhm.
and he is like defining on it some kind of like natural like the discrete dynamical system. Like he define what is a geodesic flow, but just not even like using graphmetric, just kind of on an abstract simplicial complex, which might be kind of completely arbitrary notion. Again, like mathematical theorem could be. I did not find it in his papers. Like take a Riemannian manifold, take epsilon neighborhood graph, take the graph complex of that, consider like nil geodesic. Is it actually close to any geodesic for kind of epsilon small enough? Yeah. And because he actually also kind of put some condition on his simplicial complexes, he calls a simplicial complex like Q manifold if basically every like face set, every face of the top simplex, if it has like a unique mirror on the, if it has a unique guy which glues to it, so that you can kind of like continue from this vertex to that vertex on the mirror side. And this has nothing to do with shortest path probably or something like this. I don't know. Or maybe yes, I don't know. And there is definitely one could sit down and one could like try to prove that his notion is either makes sense or not for epsilon small enough. Yeah. And also some kind of like dynamics on or some on this Rulliard, like with the rules, right? Because basically what I did in this Wolfram Winter School is basically there is like but this is actually not novel, I think novel point of view. People had these insertion brackets and how do you normally prove that it's an insertion bracket? You basically consider insertion operator. You prove that it is like how is it called, like left sesame or something like. Yes, it's like satisfy some kind of that the commutator is that the associator is symmetric into variables or something like this. And this is called like Prelly algebra, I think. Left Prelly algebra. This is like a direct consequence of the fact that if you are gluing, if you have something which you got by gluing two things together and you are gluing a third thing to it, that it can either, if you are gluing at only one point, then it can either glue here or here, you know. And the direct consequence of this is the Prelly algebra, the Prelly algebra relation. And then if you have Prelly algebra, you take commutator, and you have by algebra, you have Lie algebra. But basically, what kind of my work kind of revealed also that this stuff can be seen as like on the Rulliard, right? On the which Stephen is calling Rulliard. This is the space of generated by all the rewriting rules in this case. But we are having different the rewriting systems, but in this hypergraph rewriting system, these are the rewriting rules. And basically, if you take commutator on this Rulliard, like you view them as you view one rule as an operator, as a linear operator, which you can, right? You have it's a linear operator on the vector space generated by all isomorphism classes of hypergraphs, yeah. And you take just commutator of this stuff, and then actually this is gonna if you restrict to rules which are having left hand side, which is just one vertex or one hyperedge, nothing more. There is no context. There is just this simple left hand side, and if you take the commutator of these, you are actually getting the insertion bracket. Yeah. So basically, you can replace this proof via this Prelly algebra stuff. You can say, actually, this is just comes from commutator on the Rulliard, basically the Lie algebra structure. So it kind of got me to like thinking maybe one should do something on the Rulliard. Maybe one should, I don't know, like what one would do in physics. What's like one formulate some action principle or something like this. But if one would have some action, minimize some action somewhere to select the rules, or I don't know.
I mean, I don't know. I mean, the Rulliard is basically just the Platonic space of all the symbolic computation. Anything describable in symbols, you know, it's not something that you can do work on.
You can fix. You can take like a subset of that, right? Always you can take subsets which make sense.
If you're doing computation, then you're working in a subset of the Rulliard, yeah. Basically, but no, I mean for infinite geometry, basically stick to the points and the edges, and then develop theory from there. But this has been a great discussion. We're still live on, I don't know, it's coming up on 3 hours. I'm gonna close down this.
We are live?
Yeah. Still.
No, crazy.
I'm gonna shut down the stream. Thanks for everyone for thank you, Vit, for speaking, and thank you, Pavel, for a good discussion for infinite geometry, and thank you, Kieran, for attending.
Thank you.
Well, thank you very much for
thank you, Vit, for the fascinating talk. I look forward to your email regarding
the slides. Yes, I got them. Thank you, Vit. I got the slides.
It's very interesting. I want to learn the material. It's very fascinating. And thank you, Pavel, for the interesting discussion.
I did want to ask if you looked into geometric algebra at all. If it's possible to apply that to your Grassmannians. Vit, that was a question for you, I suppose.
Oh, sorry. I'll speak up. So can you repeat it, please?
Yeah. So
it's been a long day. So
geometric algebra is sort of like algebra of like multivectors and oriented subspaces and of vector spaces and stuff like that. Typically, it's real valued, but I mean, I don't know if there's a complex analog to geometric algebra for complex spaces, but if there was, it might be useful somehow.
Yeah, this is what I was proposing, right? That you can take this. Wolfram Institute is having this great geometric algebra booklet, if it can be somehow used.
So geometric algebra is like it's pretty much isomorphic to working with Clifford algebras, right? To describe some geometry.
Mhm.
In this sense, there should be complex version as well. Yeah, but I'm not really familiar with this formalism, so yeah, I don't really know what stuff can one do with it. But yeah, maybe it's worth checking out.
Yeah, I think it's a very broad area. This is Geometric Algebra for Physicists by Chris and Anthony Lazenby. Oh,
Yeah.
and I've also been trying to learn this material. It seems like it's very broad. It's Clifford algebra, vector analysis, quaternions, everything. It seems like it covers all of them nicely. So yeah, I think that's a great idea. I think, Dugan. And I know what's his name? Let's see. Hayes.
David Hestenes.
David Heston. Yeah, he got this 2002 Ørsted medal in 2002 for developing this. He has a long-term plan, I think, to bring it into basic mainstream education, because he thinks that this is much more powerful and much more inclusive than vector analysis, which is usually taught in schools. And
yeah. So I don't have experience with geometric algebra per se, but so for this work at Huawei, I was really concentrating on something that's easily implementable in Python, because that was or MATLAB, like these are the languages of choice for these numerical optimization techniques that we were using. But in my like pure math research, what I was doing was I was playing, for example, with these exceptional Lie groups and like projective spaces over octonions, and there I could really like if you try to do it like vectorially or with matrices, you drown because it's just too big. And like for numerical stuff, sure, but once you try to prove something by hand, you really need good formalism. So without octonions, without these division algebras, you would be really kind of screwed. But with good formalism, you can get quite nice results, which are relatively concise. Yeah. So it's kind of it's just, so my impression was that geometric algebra is a tool, right? So I just haven't encountered a problem yet where I could really use it to my advantage.
Paul, did you say there's a Mathematica package for geometric algebra?
Yes, recently Nick Musin made
Oh.
Mathematica packlet.
Yeah, I think I saw that. I think I'll look into it.
So Pavel, I was also kind of thinking when you were doing this insertion bracket. Yeah, so it's been a long day, but I vaguely remember there is some kind of like operative homology. Like you look at these graphs coming from operats and like joining operats. There is some notion of homology and cohomology. Is there something that may be worthwhile checking out in your case for these hypergraphs?
Yeah, we first needed
no idea
to make like a operators for boundary operators, and for instance.
What do you mean now? No, by boundary operators?
It takes like a little subset, and then you need to define what the boundary of that is, and then you're off doing like cohomology as an extension of that, or homology.
Which homology?
Homology.
Yeah, but wait, but why do you want like you mean like to define like simplex or something like this in this or what in what sense do you need yeah, you mean like boundary operator? There is boundary
Boundary
operator on
operators,
graph.
yeah.
There is of course yeah, but on a graph there is boundary operator, right? The kind of the adjacency matrix is kind of defining a boundary operator like signed adjacency. No, on the yeah, there is definitely at least on this clique complex of a graph, there is a boundary operator. Whether it is signed or not, adjacency or incidence, I'm not sure. So there is even like all Hodge decomposition on a graph. There is even like Hodge Laplacian. That's why I was kind of thinking of doing the discrete Chern-Simons there. And yeah, but this is like a theory on a single graph. This is something what Stephen would say that he's not interested into, because he's interested in kind of in this like bulk behavior on this kind of description of the universe.
No, but when you want to invent some observables, then like some cohomological invariance can be one thing to look at. But the question is if it's really computable. I mean, in terms of complexity.
I think at this stage we are like trying to understand like some very basics of that in some kind of like formal language and some more formal framework. And so this will definitely come when we kind of see